So far, not many people heard of this paper yet. I know the last year the Boram gave a talk here, the previous version of this. So this is new topic. So if you delete bipartite, the last two topic was there's no bipartite. So today I'm going to briefly review the background story and then some story and then explain about the construction. But when I give a talk about this last year in China, my talk became very terrible. The reason is when I try to explain the construction, it seems everybody got lost. So today I'm going to spend a little time with construction because maybe it's not easy to explain in a short time. But if you have a question, if you have any question, then you can ask me anytime. So today, I'm going to explain about the construction of a bipartite graph whose squares are not chromatic-choosable. So first, I'm going to explain what is the meaning of a square. So square of graph is, so we define this way. So the vertex are same as original graph, and then two vertex are adjacent if their distance is m-2. So left side is original graph, right hand side is the square of graph. And then here tree. Tree is very simple, but square of this tree can be very complicated. So this vertex, distance 2, so they make adjacent. But this is not final stage yet. And then, all right. So the left side is the final stage of this graph tree, and then the final stage of the original tree become like this. So this means even the original graph is simple, the square graph could become very complicated. So Peterson graph can become complete graph. And then chromatic-choosable meaning is if the least chromatic number is the same as chromatic number, we say the graph H is chromatic-choosable. So interesting question is which graphs are chromatic-choosable? So a simple example is complete graph and cycle, and their least chromatic number is same as chromatic number. And also Peterson graph is the least chromatic number is 3. And the very famous result is the line graph of complete multipartite, complete bipartite is chromatic-choosable. But in generally, complete bipartite is not chromatic-choosable. As you know, the least chromatic number can be arbitrarily large. And then another simple example. So this graph is chromatic number is 2, but the least chromatic number it becomes 3, right? So worst case is like this: 1, 2, 1, 2, and then 1, 3, 2, 3. Correct? Yeah. So this vertex, we should choose 1 and 2. So we can say, okay, how about this? Then we have to use 3 here, also we have to use 3 here. So conflict. So if you choose 2 and 1, then this side has problem. So in general, computing the least chromatic number is difficult. So in general, answer this question is not easy in some sense. And the most famous problem around this area is the least coloring conjecture. That is, every line graph of G is chromatic-choosable. Actually, this graph is famous result in the least coloring conjecture problem. And then there's an interesting question that is by Kostachka and Udar. That is, so for every graph, the square of graph G is chromatic-choosable. So one positive intuition. Okay, if we make a square, then we can see the structure become very complicated. So from our intuition, if structure is very complicated, then the possibility of, the least chromatic number is very similar to chromatic number. I think that's our intuition in some sense. But the chromatic, also, okay, and let me review the coloring of the square of graph G is trivial lower bound is delta plus 1, trivial upper bound is delta squared plus 1. And then, because the structure is a little complicated, it's not easy to compute the chromatic number. And there's several research about computing chromatic number of square of G. There's a conjecture that is, if G is planar, then I'm not sure this 2 delta or something like this. I cannot remember the full statement clearly. If this is at least 7, also, okay, the very smallest case is if its graph is subcubic, then square of G is m must 7.
Delta here is delta of G squared?
Yeah, delta of G squared.
Ah, okay.
No.
Oh, delta of G?
Delta of G.
Delta of G?
Yeah.
Huh. Even for the first one?
This one?
Oh, yeah.
This
okay.
G is planar.
Oh, yeah. Oh, if it's planar.
Yeah.
Okay. Oh.
So Peterson graph is forbidden.
Yeah. Okay.
But very interesting case is still this. Oh no, it's just 3. So still this case is open. The one interesting story is the
Which case is open? So both are conjectures. I see.
Yeah. So Cotton Thomason claimed early 2000, so he proved this. But for several years, his paper doesn't appear, or any preprint doesn't appear. So it turned out he found some mistake. So by chance, I looked at the preprint, and the proof structure is very complicated, and then, so people cannot. I mean, it's not easy to understand the proof idea. So now he said, okay, he didn't prove yet. So that's why this tells how much this problem is difficult in some sense. And then, so what is the motivation of the least square coloring conjecture? Actually, this conjecture is the conjecture what I mentioned just before. The original interesting conjecture is the least coloring conjecture. That's the every line graph is chromatic-choosable. And there's also least total coloring conjecture. I mean, we want to color vertex and edge at the same time. And then, so Borodin, Kostachka, Udall suggest, say, and that every total graph is chromatic-choosable. And then later, they make another conjecture that is every least square coloring conjecture. So what is the motivation of this? Okay, I'm going to. Actually, the least square coloring conjecture, if least square coloring conjecture is true, then it implies least total coloring conjecture is true. This is the motivation. So here's the example. So the original graph, and then the H is, we subdivide each edge. And then make a squared H squared. Then coloring of total graph of this is exactly coloring of square of H. The reason is, for instance, okay, here X and E1, they should have different color. So here X and E1, they are adjacent. They should have different color. Also, E1, edge and E1, E2, they are incident. So here, in the square of H, the distance is -2. They should have a different color. So key point is total graph of coloring of total graph of G is exactly the same as coloring of H squared. So this is motivation. But least square coloring conjecture is in some sense very too strong, because I mean we just need this conjecture is true only for very special case of bipartite graph. So because if we subdivide every edge, then it becomes bipartite. And another condition, if you have bipartite but one side, in the one side the maximum degree is just 2. And then, so last year, Boranbach, I discovered a counterexample for the conjecture. So what it did was, there's a graph for every prime n, there's a graph G such that G squared is exactly complete multipartite. So it is, there's n vertex, n vertex, n vertex, n vertex, and the total, this how much is 2n minus 1 set, and then each set has n vertex. So we have such complete multipartite graph. So it's a well-known fact this graph is not chromatic-choosable. So
Is what?
Pardon me?
Sorry, it's a well-known fact that this graph is
not. This is not chromatic-choosable. So here, also another fact is as n goes infinite, then the least chromatic number goes infinite. So the gap between least chromatic number of chromatic number goes infinite. So original conjecture was they should equal here, but surprisingly the gap become arbitrarily large. So maybe in some sense very I don't know I don't know if I say like this very too much rough conjecture. But here the point is we didn't expect there's this type of graph. I mean, it was very hard to imagine this kind of structure happen. And then, so last year, when I sent an email to Shooting Ju that we discovered such example, and then Shooting Ju asked me, so why don't you come to his place? And then, so I gave a talk in a workshop, and then, so he suggested another problem. So, okay, when k is 2 is not true, then what happens if k is very big? If k is very big, then structure will be more complicated than maybe possible.
If k is really big,
Yeah.
the result becoming some complete graph.
Yeah, but yeah,
But this is constant k.
constant k. The question is constant k for every graph. So as you said, if the diameter of G is t, then G to the t is just complete graph. So actually this observation is one positive intuition. And then from the counterexample of the least square color conjecture, we know this k should be at least 3 if such k exists. But very interesting case. Another, again, it's not true. So we found for every k, there's always bad guy. Also, very similar time, a student of Illinois group, they discovered, they construct another example using our previous example. But our construction uses Cayley graph structure. And then they use our previous, they modify our previous construction.
Who's one?
권영수. And then, so now let's return to original conjecture. So least square coloring conjecture is not true in general, but actually what we need was the least square coloring conjecture is true for bipartite graph, very special class of bipartite graph. So, and so far every counterexample of least square coloring conjecture is not bipartite graph. So you make suggest, okay, is it true for every bipartite graph? And actually one referee suggests this question. Oh, so, and Boranbach and I, oh, that's a good question. So, okay, let's try to do something. But for bipartite graph, we are not sure if this is true or there's counterexample. And then, luckily, we discovered another bad guy. So we discovered G squared is between these two graphs. So if this is true, then chromatic number of G squared is at most n squared plus 2n minus 1, because it's complete multipartite. And then least chromatic number is at least this many. And then this value is greater than this value when n is at least 7.
Wait, so this first line should be not equal, right?
Oh.
Oh.
Right. Otherwise, both are true.
Well, yeah, suppose that's true.
Yeah. Okay.
That's exciting. That's something I did before. Yeah, okay.
Thank you. So we discovered there's bipartite graph whose square is not true. It's not chromatic-choosable. Okay, so far, okay?
Can I ask? Okay, no, I know. G squared is in between those two.
Yeah.
I see.
But do you know the number of vertices of G squared? I mean, what is like kn squared is like n cubed vertices, right?
Yes.
And the other one is like n cubed plus 2n squared minus n vertices.
Yeah. So as a subgraph.
I just
So it has about 3n squared vertices. N cubed vertices.
and least n cubed vertices.
But the order is still n cubed. Yeah, it has n cubed.
Okay, the structure is like this. Actually, this is kn n squared, this part, top part, bipartite graph. Bottom, just 2n minus 1 set. So we know this is complete multipartite, but also we know this is complete multipartite, but you are not sure the relationship of this. So worst case is everybody is adjacent to each other. So that's why this is G squared situation. So G squared is a subgraph of this graph, but contain this graph. Again, still the gap between the least chromatic number and chromatic number can be arbitrarily large. And so now let's talk about construction. So construction, the main key idea is using orthogonal Latin square. The key point is, in the G squared, the complete multipartite, we need to have K13 structure, right? In the G squared. But by intuition, okay, to have V, X, Y, G, and W1, W2, W3. We make a square, so we know we can construct this structure partially, but problem is always also we have W1, W2, W3. Then how can you handle this? So this observation, from this observation, so originally we thought having this structure is impossible. But so luckily, using orthogonal Latin square, we realized this kind of structure is possible. So orthogonal Latin square is there's a Latin square here, and then so each pair, I mean the 1, 1 appear only one time in the 9 choice, and 1, 3 appear only one time. And then if n is the prime number, then we know there's n minus 1 orthogonal Latin square. But there are several types of orthogonal Latin square. But actually, in our construction, we use this Latin square. So I'm going to skip a detail. And if n is 5, then we have 4 Latin square. They are orthogonal each other.
Yeah.
Yeah.
What is the definition of orthogonal? Can you say that again? Orthogonal?
Orthogonal?
When you superimpose them, you see all 5 times 5
Yeah.
combinations.
Yeah.
Okay.
Yeah.
Right.
Yeah. Right. Like this.
Yeah, like that.
Uh-huh.
So this is the one you get from the standard construction of the finite projective plane.
Yeah.
Using just the field on P elements, right? This is the standard set of orthogonal Latin squares that you get from this standard projective plane construction. Yes.
You mean that this Latin square come to projective plane?
Yes.
No. Yeah. In some sense, some orthogonal Latin square are related to projective plane, but we use this. So I think this is not related to projective plane. But maybe you are right.
We can discuss that.
Yeah. And our original construction are like this. We have a P set in the top, N set, the n minus 1 set in the bottom, and each set contains n vertex. And then we need to define the neighborhood of W11. Then the neighborhood is exactly follow orthogonal Latin square list. So here, example. We have this is smallest counter example of the least square color conjecture. And then we have 2 Latin square L1 and L2. And then neighborhood of W11, it is this way. Just look at the bold number. So 1, 2, 3. It is 1, 2, 3 here. Here 2, 3, 1, just 2, 3, 1. 3, 1, 2, just 3, 1, 2. And the second set, 1, 3, 2 is same as 1, 3, 2. 2, 1, 3, 2, 1, 3, 3, 2, 1, 3, 2. So if you do this, then because of orthogonal Latin square, every 2 set, their distances, and they have a common neighbor actually. Because of orthogonal Latin square structure, every 2 set has a common neighbor. and then the common neighbor. Yeah, and also because of that structure, we can show it become actually this way, K333. I mean the G squared is K333. Yeah, actually. So let me repeat again. So W11 is adjacent to this way. Just here, look at W11 is okay. We need
Wij, it means
Yeah.
row I of box J or something.
Yeah.
Yeah. Or opposite.
Yeah. I mean the I is orthogonal Latin square and J is low. Just here, W11 is adjacent to W23. Why? W11 is 1 to 3. 2, 3 is. So they have a common neighbor W22, V22.
This doesn't really use any particular properties of the family of orthogonal Latin squares that you have, though.
Yeah, basic. I mean, yeah.
Yeah, right.
You're right.
Now you're just using that as a finite projective plane.
Yeah.
Yeah. This is a very small case, so maybe this case, maybe we don't have to use the definition of orthogonal Latin square.
Sorry. No. I'm assuming that you're using the definition of orthogonal Latin square, but you aren't using any particular construction of.
Also,
You can take a different set of orthogonal Latin squares, not the one that you gave.
Yeah.
You gave a specific set, Li.
yeah.
But so far, to get this K3333, you can take any orthogonal set.
No.
Really?
No. I mean this is a small. I mean when n is 3, I mean any orthogonal Latin square is okay in some sense because very small size. But if n is big, we need some. Not every orthogonal Latin square will work. That's one difficulty when you prove it in general. So we try to find one good orthogonal Latin square. I mean what we need was no, let me just think of it. Just look at this line. Okay, look at the first two lines here. Do they have a common pair?
No, because you just shift the second column.
Yeah.
So
Yeah.
you never have common. Yeah. Is that the property?
Yeah. So we want to. Okay, let me think more biblically.
Yeah.
If you compare any two columns, then no common pair appear. If you look at this column, compare first and third column, then any pair can appear only one time. Here, and then here.
Oh, you mean that if you have a 2 and then a 4, you
Yeah.
can't then see a 4 and a 2?
Yeah.
Okay. Oh, so that is a property that's special about it.
Yeah.
So if you see 2, 4, you can't later see 4, 2. Okay.
No. Same 2, 4. The 4, 2 might appear. Right?
Yeah.
What?
So you
I don't
don't.
know.
No, you can't have. A 2 appears at most once in a given column.
Yeah.
Like just the definition of a Latin square.
I mean, you have a set of Latin squares. If you have a 2-4 pair in one Latin square, you don't want to have the 2-4 pair in a different Latin square at the same column. Same set of columns. If you take the first 2 columns, for instance, if you don't have a 2-4 in the one Latin, if you have a 2-4 in one Latin square,
Right.
then all other Latin square doesn't have 2-4
Okay.
in the first 2 columns.
I see. Okay.
Is that what?
Oh, okay, here, let's look. Okay, let's look. If neighborhood of this, then these 3 vertex, it become complete graph, right? Locally. And then if you look at here, then these 3 vertex induce complete graph. So we want to show no edge overlap.
That's it.
Yeah. So what happens if some edge are common? What does it mean?
If some other edge will be missing.
Yeah.
Like counting.
I mean, if some edge, I mean, if 2 vertex appear in the same neighborhood, I mean, here and here, I mean, what does it mean in the also Latin square? That means actually,
And you have n square pairs,
Yeah.
potential pairs,
yeah.
some pair is missing. So one pair is used more than once.
Okay, let's do this. The 2 Latin square. Then there's 2 columns, maybe CI, no. CA, CB. Here, 2 column CA, CB. So here, what happens if have 1, 2 appear here? Maybe different location, 1, 2 appear. So it means, what does it mean? This. This is QI, QJ. Okay, this meaning is this vertex adjacent to 1, 2 here in some sense. And this meaning is this vertex also adjacent this way. Then this and in the square, I mean the point is this edge appear in this vertex and this vertex.
In the square.
Squares. And that situation is exactly the same as in the also Latin square Li. The pair 1, 2 appear here. Also another place 1, 2 here. But some orthogonal Latin square have this situation. So we cannot use such orthogonal Latin square. Okay, so we can talk about this after this. So okay, like here, so we want no common edge. So and then for our new construction, okay, this is original construction shape, but in the original construction we have a complete graph, subgraph. So it's not bipartite. So to make bipartite, we need to remove complete subgraph. Okay, instead, so we add another set. In the square, S1 adjacent to top vertex. So in the square, these three vertex are just complete. These three vertex induce complete graph, subgraph. So in this structure, we know top vertex, it become complete multipartite with n set. Bottom vertex, so we guarantee, okay, at least this here, but it's not important actually. 2n 1. Ah, 2n. We know bottom vertex induced another complete multipartite. The problem is, problem is, so we don't know relationship between. So maybe this graph is already counterexample, but it's not easy to compute the least chromatic number. But still, but here it's not what I'm talking about. Oh, it's just n star n. Sorry.
Jonathan, isn't
Yeah. Yes.
isn't this sorry? Isn't this vertex joined to everything in here in the square?
No. In the square, this what? Yeah.
Sorry, is this vertex joined to all of this in the square?
Yes. Okay.
Oh, it is. Okay. Oh.
Let me show you.
Yeah. No, I think I believe that.
In the square.
In the square.
Square. Yeah.
So here, look at the 2, 1. Already adjacent to 3,
Yeah.
and V2, 2.
Right, because you could go to the sort of row and
Yeah.
go over.
Because everything is adjacent to each other. So this vertex adjacent to this vertex. The distance 2.
Yeah.
Yeah, but that's in the original construction.
Original.
The new construction, delete this edge.
In the new construction.
So how do you go like?
I see. Okay, I know. We don't know. But I'm talking about only top part become complete multipartite. I'm talking about also bottom part also complete multipartite. But as you said, we don't know relationship between here. So at this moment, what is the chromatic number of this? Okay, we can say n because 2n set. But what is the lower bound of least chromatic number? How much guarantee? Maybe very safe case because it contains k n star n as a subgraph. So we know this, but this value is not high enough than this. So we cannot say this is counterexample yet. So, but maybe already this is a counterexample if you're able to compute the least chromatic number nicely. And so to complete the counterexample, so we add several copy. I mean, this is original case, small. And this one and this one is original small case. And then we add the top part, two more. We copy two more top. And to make some adjacent, to make a nice relationship, we add another one. And then their behavior is the same as the original construction. So here look at every vertex here adjacent to each other. I mean this vertex adjacent this vertex adjacent this. Also inside here, it becomes complete multipartite. Inside here, complete multipartite. The problem is, can this vertex adjacent to this vertex? We want to make this vertex adjacent to this vertex. So to do this, we introduce new vertex. And then the neighbor, the pattern of a neighbor the same as W11. I mean, every vertex here adjacent, I mean, the W11 is adjacent every vertex here, every vertex here, every vertex here. Just imagine. Then this vertex, this vertex, this vertex induced complete multipartite because they have a common neighbor of W11. Okay, so time is passing. So anyway, so by copy on the top part, and then we can show instead of this, okay, n squared, and then this n squared is least chromatic number n is big enough to obtain the counterexample. So that's why, so through this way can complete the computation. And then we want to make another discussion. This is for new problem. So let's define BK is the bipartite graph, which one set has maximum degree n must k. Actually, least the total color and conjecture is true if this is true for every graph in B2. The reason is subdivide each edge because one bipartite has maximum degree just 2. So question is there some k such that every graph in BK and the G squared chromatic-choosable? If k is 2, it means at least the total coloring conjecture is true. But our construction say actually the maximum, the k is 13, so in the top part, the maximum degree is 13. So if it's true, also, but we can modify our construction such that we can reduce the maximum degree in the one set up to 7. So it means if such k exists, then it's at most 6. But at least 2. So question is, which is correct number?
If it's true for k is 2, I mean, you said that if it's true for B2, then it's LTCC is true.
Yeah.
But is the converse true as well, or is it equivalent?
I think equivalent. Yeah. So, okay, so this construction. And then, so let me introduce another problem. So last year when we discovered the Konkuk example, Jonathan Noel suggested another problem. Okay. Conjecture was this is equal. These two values equal, but our construction say, okay, this is not true in general. Then what is the upper bound, in general upper bound of least chromatic number? So he suggests, okay, this could be one good candidate. And this candidate came from our construction actually. The reason is complete multipartite, the least chromatic number is upper bound is this value. Just from this value, we have this format. So another question is, okay, is it true? I mean, for every, this imply least total conjecture. Or is it true for B6? I mean, so far our construction say to make a counterexample, the degree should be a little, we need a high degree. But if the degree in the top very small, just 2 or 3, then maybe it's true. Yeah. Okay, thank you.